In this lecture, we're going to continue our discussion of principles of measurement by focusing on some additional key definitions when it relates to measurement principles in research. And on this slide here, we're going to contrast the difference between discrete and continuous variables. A discrete variable is defined by one in which a measurement is done so in units that cannot be subdivided. And so these are units of the measurement that contain gaps between those units. And as such, these variables are classified in whole units or whole numbers. So there are no fractions, and we'll take a look at some of these examples. So some of the terms that you'll be familiar with include what's called a dichotomous variable and categorical variables. Specifically, a dichotomous variable is one that only has two possible outcomes. So for example, if one wishes to classify research participants as male or female, and that is the limit of the categories, then that would be a dichotomous variable. Another example of a dichotomous variable is one where the possible outcome could be yes or no to a question. The scores, as indicated, usually take the form of whole integers if the outcome measurement is quantitative in nature, so that a numerical value is applied. And one example here of a measurement that would be classified as a discrete variable would be the number of people per household. And so the number of people living within a particular household would be scored as a whole number. Of course, coming back to the dichotomous example here, of course, this is not a new. This is these are word descriptors, not numerical descriptors. A continuous variable, in contrast to a discrete variable, is one in which the measurement can be subdivided infinitely. And as such, the variable can take on a value along some continuum. And so there are no gaps between the possible scores or the possible outcomes like we saw with a discrete variable. So with a discrete variable, we clearly see that there is a gap between 0 and 1, 1 and 2, 2 and 3. And so in this particular type of approach, if we're using a discrete variable, we cannot have an outcome that's 0.5 or 1.3. So coming back to our continuous variables, in theory, now again, this is just in theory, these are variables that have an infinite number of fractional components. Now, of course, we know in reality that's not true when we apply it to an actual testing or measurement instrument. And as such, the numerical value taken along a particular testing instrument is limited by the precision of the instrument. So as an example, very often age is quantified in years, but we can be more specific and more precise. So we can measure age in terms of years and months and weeks and days and hours, and so we can see that in that application, age can take on a more of a continuous property. A couple of other very important definitions to understand when it comes to research study design and measurement is that we have to first determine what the outcome measurement of interest is, and that's what we call the dependent variable, and we'll work through an example here. So in this example, imagine if we're interested in the outcome, the results of a federal election. Now, these are not real political parties, but I'm just using colored terms here to indicate three different political parties. And so in this, if we're counting up the results of a federal election, we might tabulate 68 seats for the red party, 34 seats for the blue party, 20 seats for the purple party. Another example of a dependent variable in terms of the ultimate statistic, the ultimate numerical value of interest, might be the number of SARS-CoV-2 infections in Ontario. And as of June 3rd, 2023, the Ministry of Health for Ontario has tracked over 1.6 million cases of positive SARS-CoV-2 infections. And so what we're looking at here is the greater than 1.6 million number of cases is the actual final numerical value that we're interested in, as is the number of seats for each of the three respective parties. Another example here is the median household income in Ontario. So once again here, based upon our question, what is the final number? What is the number we're going after here? And it's the $74,260 is the outcome measurement. Now the dependent or outcome measurement, the value here depends upon other sorts of things. Those other sorts of things is what we call the independent variable. So the independent variable is a factor that influences the outcome. What is the outcome? The dependent variable. So the outcome of the dependent variable depends upon the independent variable. So if we go back to our three examples here, the three bullet items, in terms of the independent variable, we see that the dependent variable indicated in the first example up back here at the top of the slide is the party share of the votes. So the red party picked up 68 seats, the blue party picked up 34, the purple party picked up 20. Now the factor that determined which party got these number of seats, one of the factors, one of the independent variables, might be political campaign fundraising. Now, this is something that is just one independent variable that could have influenced the outcome of the election. But it's important to note that political campaign fundraising is not the only factor that would influence the party share of votes. There are many factors, but this is just one of the factors. So that highlights an important aspect of understanding independent and dependent variables, is that there can be more than one independent variables that influences the outcome of a research study or some other question of interest. With our second example, with the number of SARS-CoV-2 infections in Ontario, once again here we start on the second half of this bullet item, where the number of SARS-CoV-2 infections listed up here is our dependent variable, and an independent variable that influences that might be residential location. And so once again here, as we saw with political campaign fundraising, based upon residential location, that has been shown in some studies to influence the number of SARS-CoV-2 infections. And finishing up with our third example here in terms of household income, one of perhaps many independent variables includes the level of education of the members of that particular household. So once again here, when we take a look at these three independent variables, these three independent variables will have an effect and determine the outcome of the dependent variable. To understand these different or the different ways to quantify items of interest is to first understand measurement scales. And so there are 4 measurement scales, and we're going to present them here in terms of the simplest to the most complex. And the simplest scale is just simply called a nominal scale. And a nominal scale of measurement essentially just identifies different scores. And if we apply a numerical value, and we'll take a look at an example here, or some examples here shortly, the nominal scale does not actually measure an amount or assess a value to these scores. But all the nominal scale does is just classify groups or responses. And so some examples here include a question that would be posed to the general public or to sports fans, is whether professional athletes make too much money. So we would ask people if they think if this is the case or not, and so we would just ask the question, do professional athletes make too much money? And this is a nominal scale in which the participants of this study, which would include the general public, would just simply answer yes or no. And we see here that the outcome is one is no more valuable than the other. But what we're doing here is we're just quantifying, or at least classifying, the attitudes of the general public as to whether they think athletes make too much money. If we define sex at birth as male or female, if we do it this way, that would have only two categories. And so once again here, what we see is that one is no more valuable than the other, and there is no measurement of the amount here, but we're just simply classifying sex at birth with two categories. If we classify sex at birth as male, female, or intersex using the variant definition here, then what we see here is we have three categories, and all we're doing here is we're counting the number of occurrences within the three categories. If we define gender as man, woman, or non-binary person, so once again here, one does not have a particular value different than the other, and we're just classifying those based upon those three categories. And these latter three bullet items have been defined by Statistics Canada, and we can see here that this is the link to the website to the federal government that established these three categories. So once again here, we don't have a numerical value, we just have categories. So the nominal scale, to summarize the nominal scale must satisfy three criteria. The first is that it must be mutually exclusive, and so there must be one and only one category for each case. And so going back to our first bullet item, a person cannot answer yes and no at the same time. So the outcome is categorized in one or the other. That's what mutual exclusivity refers to. The nominal scale must also be exhaustive, which means that there has to be a category for every possible outcome or score that might be found. And so once again, we go back to our first bullet item, and we have an exhaustive scale. And so this, although we can probably reword this question a little bit differently, but if we carry out a study using this specific question, then we can see that we only have two categories, meeting the exhaustive property here. And the nominal scale must be homogeneous. And so what that basically means is that the categories should include cases that are comparable. So all of the yeses will only include yes. All of the no category will only include no. Moving up one level from nominal is what we call the ordinal scale. And one way to remember the ordinal scale is that it's ordinal. We're applying some sort of order to our outcome measurement. We did not have that with a nominal scale, but with the ordinal scale, what we're doing here is we're now rank ordering the outcomes. With the nominal scale, there was no logic to assigning a particular order. So with a nominal scale, listing the categories could just simply be done in an alphabetical order manner, and the order did not have any particular value to it. But with the ordinal scale, indicates a position, a relative position between the items, and we'll take a look at a specific example here shortly. So some examples of an ordinal scale might be opinion surveys, where some opinion surveys on a product or a service would have a number of possible categories that one may rank order as strongly agree, neutral, disagree, or strongly disagree. And in the example here, we have a clinical measure of muscle strength indicated in this photograph. So here we see a physiotherapist assessing the knee flexor strength of a particular athlete using a manual resistive technique. Now, based upon the experience of the physiotherapist would rank order the strength of the athlete and rank order it in terms of grade. And so the clinical measurement of muscle strength has grades from 5 to 0, where 5 is the highest level. And the highest level would be classified as normal strength. And what we see here on this table is that even though we have an ordinal scale, we can still generate very full and clear definitions for each rank on the scale. So where the 5 indicates a complete range of motion against gravity, and the athlete will, or the athlete or patient is able to activate their muscles against full resistance. On the far bottom of the scale is a grade of 0 muscle strength, and that's where the athlete cannot even contract their muscle. And so we have the scale with a graded level of improvement in muscle strength from the 0 up to 5. Moving up one more level is what's called the interval scale. Now, the interval scale is where we start to apply numerical values and we start to count the amount of whatever it is we're trying to measure. Now, the interval scale is called interval because there's an equal separation between the scores, hence interval. The interval scale is unique in that values can take on negative numbers, and if we can take on a negative number, there is no true 0 on this scale. There is a 0, but the 0 represents a reference point that separates the positive numerical values from the negative numerical values. And so some examples here include the one that's that people are most commonly familiar with is temperature, whether it's Celsius or Fahrenheit, but we measure temperature in positive or negative values. Or financial status, and the unit of measurement here would be dollars. So with these two examples, the variables would be temperature in our first example and financial status in our second example. Those are the individual variables. Now, the measurement of temperature, the measurement of financial status would require units. So the units for temperature would be Celsius or Fahrenheit, depending upon which scale a person would use. And for financial status, it would be dollars. Now remember, we can take on negative values for Celsius or Fahrenheit, but can we take on negative values for dollars? And we can. If we're measuring financial status, a positive dollar value would indicate a person or a business is in a state of excessive dollars surplus, or they're running a negative balance that would be a financial deficit. And so we see here with the interval scale, we do have that one of the key characteristic is that the values can be positive or negative. The fourth and highest level is the ratio scale. And the ratio scale represents the truest amount of the variable that is present. So this is also the case with an interval scale, but the difference between the interval scale and the ratio scale is that the ratio scales is scaled to a true zero. So some examples of a ratio scale would be employee salaries or age, where we see with employee salaries, if the salary is zero, the zero would indicate the absence of any salary. So the employee is not generated a paycheck. So the employee cannot have a negative salary. And if we track age from the point of birth, we don't have a negative value for age. It's scaled from zero. And what we see here to keep in mind is that the interval and ratio scales, these latter two scales, there is some overlap. And to differentiate that overlap requires the variables temperature, financial status, employee salary, age in a research study be very clearly defined with a great deal of precision. And speaking of precision, it is another indication or another important property of any measurement that refers to the exactness of a measure and is often a function of how sensitive the testing instrument is. And as an example, if we want to measure heart rate, oftentimes heart rate is measured in whole numbers, and that's what we see here on the right hand side in this picture. This is a standard heart rate monitor that a person straps across their chest when they're walking or doing any other type of physical activity, and this watch displays a value of their heart rate in whole numbers. Surveys and questionnaires should also be assessed for the degree of precision. Now, the one key aspect specific to surveys and questionnaires is that these often present a limited set of options or categories. And so researchers often struggle with how many categories or options are considered to be optimal for a survey or questionnaire. So should they add more categories? Sometimes adding more precision does not provide any more useful information. Too few categories, too little precision doesn't provide the requisite amount of information that the researchers would be looking for either. So whether it's a survey, questionnaire, measuring heart rate, or any other variable, there is an optimal level of precision that provides enough information to the researchers, but not so much precision that it begins to lose a degree of meaningfulness. So this ends our second part to our unit on principles of measurement.